Okay, now that we've discussed the first law of thermodynamics, we're ready to talk about engines. Okay, now at the heart of every engine, basically what's happening is you have some working material, working substance. Okay, it absorbs heat. Okay, so you have a working substance. Okay, and what happens is the working substance will absorb heat. Okay, then it absorbs heat, it'll expand, and it'll end up doing some work. Okay, and then after the work is done, it will release heat. Okay, and come back to whatever state it was in the beginning. For instance, in a steam engine, okay, the working substance will be water. Okay, you heat up the water by, you have a boiler, you heat up the water heats up, turns into steam. Okay, the expanding steam does work on the pistons, and then the as it does work, it releases the energy. Okay, the steam will condense, it'll turn back into water, and then it'll go through the whole cycle again. So every engine works in this principle. Now if you have, we can schematically show this in the following manner. Okay, so we have a hot reservoir, a cold reservoir. Okay, and what's happening essentially is this: you have a process. This is the pipeline. Okay, so some amount of heat, Q hot, okay, is absorbed from the hot reservoir. Okay, the engine does a certain amount of work. Okay, and at the same time, a portion of the heat is also released to the cold reservoir. This is the exhaust gas. Okay, now the second law of thermodynamics places restrictions. This QC can never be zero. Okay, at the same time, you cannot have the reverse of this process happening, where all you do is absorb heat from the cold and put it into the hot. Okay, so that's not possible either. So anyway, so those are all some restrictions on the second law. Now this is the working cycle for an engine. Okay, now we will be interested in something called efficiency of the engine, and the efficiency is simply going to be equal to the work done divided by the heat absorbed. Okay, but now what we also know, if you look at this process, we know that the heat absorbed is equal to the work done plus the heat released. Okay, now in calculation we'll see that when we calculate Q for processes where heat is being released, it will end up being negative, and that will imply that it is heat release. Okay, so that's why we're just taking absolute values of everything. All right, so we can also write E as, if you see, W is QH minus QC, so we can write as QH minus QC divided by QH. Okay, and I can rewrite this as 1 minus QC over QH. So this expression right here and this essentially are equivalent. They're the same things, okay, just written in slightly different forms. So this is what happens in a heat engine. All right. So let us take this and apply it to a problem. All right. So here's the problem. We'll start with a process of this sort. We have V0. Let's say this is P0. Let's say this is 2V0. Okay, let us say this is 2P0. And we take a gas from A to B, B to C, and then from C to A. Okay, and we can ask a bunch of different questions. Okay, our ultimate goal here is to find the efficiency. What is the efficiency for this cycle? Now the question is very simple. Okay, however, this is going to be a long, lengthy process, so stay with me each step of the way. And what I would like you to do is, when I as I break it up into parts, okay, do the parts yourself and then verify your answers with me. And let's say you've been given 1 mole of an ideal monatomic gas. Okay, so this is 1 mole of an ideal monatomic gas, and we're going to take it through all this cycle. We're going to figure out the work done for the cycle. Our ultimate goal is efficiency for the cycle. So let's do this. Okay, so in order to achieve this, what I'm going to do is I'm going to break it up into cycles, into processes. First, I'm going to take process AB, And I'll repeat this for all the processes for AB, BC and CA. Okay, and what I'll do is for process AB, I will calculate the work done. I will calculate the change in the internal energy, and I will calculate the amount of heat absorbed or released. Okay, if it's positive, it'll be absorbed. If it's negative, it'll be released. So we'll do this. Okay, so at this point, pause. Okay, pause the video and go ahead and do the calculations. Okay, I'm going to continue. So first, work done. Work done is area under the cycle. Oh, sorry, area under the curve. Okay, and to find the work done, I will have to find this red area right here, all this area. Great. So what I'm going to do is I'm going to use my formula for area of a trapezoid, and since the volume is increasing, I need to put my negative sign here. So minus half of P0 plus 2P0, okay, multiplied by the base 2V0 minus V0. Okay, now if I simplify all this, I end up getting 3 half PO times VO with a negative sign. Great. So we do the work done. Now we also need to find the internal energy. So actually I forgot one thing. Before we do any of this stuff, okay, let us write down the temperatures at A, B and C. Alright, so temperature at A is equal to P0 V0 divided by NR. Temperature at B is equal to 4 P0 V0 over NR, and temperature at C is equal to 2 P0 V0 divided by NR. Great. I have my temperatures. Actually I said 1 mole of a gas. Oops. So you can just get rid of the n's. N is all 1 in all the 3 things. Okay, good. So we have everything in good form. Okay, let us find delta U AB. So for this I'm going to do 3 half N R times TB minus TA. Now we know N is equal to 1, so you get 3 half times 1 times R times TB minus TA. TB is 4 P0 V0 over R, and TA is 1 P0 V0 over R. So I'm just going to skip the step and rewrite it as 3 P0 V0 divided by R, and this ends up giving me 9 half P0 V0. Great. I know delta U, I know WAB. Let us find Q. So QAB plus WAB from the first law we know is equal to delta UAB. So therefore QAB is going to be delta UAB, which is 9 half P0 V0, okay, minus WAB, which is negative 3 half P0 V0, which is equal to 6 P0 V0. Awesome. So we got the first part. Okay. So now let's repeat all this for the process B to C. Alright, so let us find WBC, let us find delta UBC, and then also find QBC. Alright, great. WBC is very easy because it's an isovolumetric process. WBC is 0. Delta UBC is 3 half NR times TC minus TB, and this is equal to 3 half times 1 times R times TC. TC we know was 2 POVO over R, and so it will be 2 POVO over R minus 4 POVO over R, okay, which ends up being equal to, so we get a negative 2 here, the 2 cancel, we get negative 3 P0 V0. Great, which means that QBC is equal to negative 3 P0 V0. There's no work done. Awesome. So we got the second part here. Let us repeat all this for the process C to A. Okay, we'll find work done for CA, we'll find delta U for CA, and then we'll find Q for CA. Alright, so to find the work done for CA, once again we have to do area under the curve. In this case the volume is decreasing, so I know that my work done has to be positive, and this is equal to P0 times V0. That's it. Okay, now delta U CA is going to be equal to 3 half times 1 times R times TC, which is P0 V0 over R, minus TA, which is 2 P0 V0 over R, which is equal to negative 3 half P0 V0. Great. We have this. Now we can find Q. So QCA, okay, plus POVO is equal to negative 3/2 POVO, which implies QCA is equal to negative 5/2 POVO. Awesome. So we have all our steps now. Okay, all our process. We've taken care of everything. Now we just need to find our Q hot, Q cold, and then life is good. Okay, so now that we have our processes, let's figure out what is Q hot. So Q hot, okay, is equal to sum of positive Qs. Now in this case, we only have one process in which the Q is positive. Okay, so it happens to be the first process where the Q is 6 POVO. Alright, so this is equal to 6 POVO. Q cold, on the other hand, is sum of negative Qs, okay, which happens to be negative 3 POVO, negative 3 POVO, negative 5/2 POVO, okay, which is equal to negative 5.5 POVO. Awesome. So now the efficiency is simply 1 minus absolute value of QC over absolute value of QH. It's equal to 1 minus 5.5 POVO divided by 6 POVO, which happens to be equal to 0.5 over 6, which is equal to 0.083, okay, for the efficiency. So this is how we do a problem of this sort, finding the efficiency. Now you could have also find the work done for the whole cycle, but you still need to know all the individual Qs for the thing, so there is really no easy way of doing this. Alright, so that is one giant problem. Alright.